Hi everyone, it's Alyssa, and in this final video, we're going to be looking at how I created the stylized terrain. First, we'll walk through the terrain model generator, which takes in a blockout of the terrain and generates a stylized terrain model. Then we'll take a look at the terrain shader. The terrain shader also takes the original high poly model and creates a lower poly mesh that it UVs and bakes the colors into a texture for. Now let's take a closer look at the terrain model generator. The terrain model generator has two modes. It can output a preview mesh, which has several intersecting meshes that are not Boolean together with each other, or the final mesh, which is one manifold mesh. The preview mesh is better for viewing faster changes when updating settings, but the final mesh is required for feeding to the terrain shader. The user also has control of several settings to influence the terrain's overall shape and the rocks that are placed on it. Of course, the terrain's shape is primarily driven by the inputted blockout, but the user can also add noise to that blockout to break it up a bit. There are also several different types of rocks. The first are the main shape rocks, which are larger and try to fill the shape of the original blockout. The second are the crevice filling rocks, which are medium-sized rocks that fill the spaces with deeper crevices, usually at the edges of the main shape rocks. The third are the small flat rocks, which are little rocks scattered on the flatter parts of the terrain. And the final set of rocks are the bottom rocks, which help break up the shapes in the bottom of the island. The tool has a couple different controls for the various rocks, but the main ones are seed, scale, and amount. Now let's dive into the tool and see how it works. The input blockout is fed in here. Then the island's base shape is created here, and the main shape rocks are created here. These three sets of nodes create the crevice filling rocks, the small flat rocks, and the base rocks. On the left are two different rock variations, which are used throughout the system, so pretty much the entire terrain is just made from these two rocks. Now I'll walk through this process in more detail. First, the input blockout is Boolean unioned to create one manifold mesh. Then, I use a match size to center it at the origin and give it a consistent scale. I use the Labs Fast Remesh node to give the mesh more resolution before smoothing the mesh out and using another Labs Fast Remesh. I then group the bottom of the island so I can add some noise to it, and I use the Labs Mesh Sharpen node to smooth it out and give it its stylized shape. This creates the base mesh for the terrain. Before diving into placing the rocks on the terrain, I'll walk through how I create the two rocks that I use throughout the rest of the network. The networks for these rocks are pretty much identical, just with different parameters for each, so I'll just walk through the one on the left. I start with the cylinder, which I add some noise to. Then, I group the top points so I can keep them in the same place, while I scale the bottom points out to give the rock a wider base. Then, I want to chip away at some of the rock's corners to give this more interesting look. I do this by using the Labs Random Selection node to randomly select some of the top points. If I check this Color Selected option, you can see that in this case, it's picking all the points but this one. I set normals and random scales on these points, and then I copy boxes to them. If I scale down the box, you can see what's going on here. By Booleaning these boxes out of the cylinder, I get this nice rock shape. I then remesh the rock and smooth it out. I add some noise with the mountain node, and then I use the Labs Mesh Sharpen node to give it that stylized look. Then I move it down, so when it's placed, it will always be intersecting slightly with the ground and never be floating. And I set this variant attribute to 0, so that I can differentiate it from the other rock, whose variant attribute is set to 1. You could always create more rocks like this if you felt that these two rocks didn't give enough variation, but personally, I don't think I really notice it in the final terrain. Now let's take a look at how I make each of the groups of rocks, starting with the main shape rocks. To make the main shape rocks, I start by converting the input blockout into a VDB, and then using the VDB to spheres node to get a set of spheres that fit the blockout shape. I add some random rotation and scale to the spheres, and also set a random variant attribute to each one. By checking on the piece attribute and setting it to variant, I can copy a different one of my rock variants to each one of these spheres. The random rotation and scale also help add a bit of extra variation. And that's it for the main shape rocks. Now let's take a look at the crevice filling rocks. I wanted to add these crevice filling rocks to places like here and here on the mesh. I find these areas using the Labs Physical Ambient Occlusion node and the Labs Measure Curvature node. The Physical Ambient Occlusion node creates a point attribute of each point's ambient occlusion. If I visualize this output, you can see that the places I want rocks tend to have higher ambient occlusion. The Labs Measure Curvature node is also useful for selecting these crevice-like areas. If I visualize the output, you can see it also selects a slightly different area that I also want rocks in. I use a group expression to combine information from both of these attributes to create a group of points that I want to keep. Then I blast all other points. You'll notice that in addition to the larger area that I want to place rocks, it also gives me some smaller junk where I don't want to place rocks. I use the Labs Delete Small Parts node in order to get rid of these pieces and isolate the good areas. Then, I just scatter points on these areas, randomize the scale, p-scale, and rotation, and set a random variant attribute so I can copy my rocks to these points. The reason I set both random scale and p-scale is because I want to use the scale to vary the scale of the 3 dimensions independently. However, I don't want these variations to be too extreme because I don't want the rock to get extremely squished or stretched in any one direction. So I can use the p-scale to add a larger amount of variation to the scale, but ensure that that variation is uniform. Now let's take a look at the small flat rocks. I only want to place these rocks on the flatter parts of the terrain, so I use the Labs Split Prim by Normal node to isolate the primitives that are facing mostly in the upwards Y direction. I also don't want to scatter rocks too close to the edge of the terrain, so I use the Labs Distance from Border node to get an attribute that can help me identify these areas. If I visualize distance from border, you can see that this attribute gives me information about how far each point is from the edge of the mesh. Then, I use a group expression to group these points near the border, and then I blast them away. Now, just like the crevice-filling rocks, I scatter points, I randomize their scale, p-scale, and rotation, as well as their variant, and then I copy rocks onto those points. Finally, let's take a look at the base rocks. I use a similar approach for the base rocks as I do for the main rocks, converting the input blockout to a VDB and converting that to spheres. I also add a random rotation to each one, and I extract the points representing each sphere. Because I only want these rocks at the base of the island, I use a clip node to get rid of the ones at the top. I also want to be able to randomize these rocks, so I use a Labs random selection to randomly delete some of them. However, I want to ensure that the largest rocks always get kept, so I use this group expression to group the points that correspond to large spheres, and I exclude them from being fed into the Labs random selection node, so they're always preserved. Then, I offset these rocks' positions and modify their scale based on the tool settings. I add an attribute to drive the random variant, and I copy the rocks to these points. You'll notice that all these groups of rock have switches, so the user can enable or disable them entirely. Finally, I merge all the rocks together with the base terrain. This switch is connected to the tool's output mode, so if the preview mesh is enabled, it'll just output this mesh. But if the final mesh is enabled, it will boolean all these rocks together, remesh them, and apply a final mesh sharpen. Finally, I revert the terrain's original position and scale. And that's everything for the terrain model generator. Next, let's take a look at the terrain shader. The terrain shader takes in the final mesh from the terrain model generator and has 2 outputs. The output on the left is the UV'd lower poly terrain used for rendering. The output on the right is a high poly terrain with a color preview of what the shading will look like. The terrain shader has settings for tweaking the intensity of the shadows and highlights, as well as the dirt and grass. If I turn off the dirt and grass, you can see just the terrain shadows and highlights. I purposefully have these scaled up to be pretty intense so you can still see them through the dirt and the grass. But if I wanted to scale down the intensity, this global intensity scale parameter scales the intensity of all the different shadows and highlights. I can also use these sliders to affect individual parts of the shader. For example, if I don't like how harsh these highlights are, I could turn down the sharp highlights. The dirt and grass have similar settings. If I enable the dirt, I can change the dirt intensity and how much different factors like slope and AO affect the dirt. If I turn on the grass, I can change the grass's intensity as well as the direction that the grass faces. In this Materials tab, I set the path for where the generated texture should be rendered to. I also set the shading mode, which has the same options as the building wall textures. This button is used to render the texture maps to disk. Unlike the shading for other modules in this project, I shade the terrain almost entirely in SOPs. Now let's dive into this node to check out how it works. Here's where the terrain input comes in. I first use a match size to scale it to a consistent size. Then, I set a base color. I'm going to disable all viewport lighting so we can see just the effects of our texturing. First, I use some Labs Edge color nodes to add some shadows and highlights to the mesh based on concavity and convexity. The Labs Edge color node allows you to select a mask color and a blend mode. You can also change the intensity, contrast, and blur amount with which it's applied to convex and concave parts of the mesh. For this first node, I want to add some blurred shadows to concave parts of the mesh. So I disable shading on the convex parts of the mesh by turning the intensity to 0, and turn the blurring on the concave shading pretty high. The intensity of this effect is controlled by the Terrain Shader tool settings. I then do the same thing with a slightly darker, more saturated color, lower intensity, and smaller blur amount to add sharper shadows to the mesh. I do the same sort of thing for highlights, adding one blurred highlight, one sharp highlight, and one extremely blurred highlight to the convex parts of the mesh. These shadows are pretty sharp and intense, so I want to add some more gentle ambient shadows. I do this using the Lab's Physical Ambient Occlusion node. From this, I get an attribute for each point corresponding to how much the ambient occlusion is. If I check Visualize Output, you can see what this mask will look like. I then blur the mask out and use this wrangle to add color based on this color ramp driven by the ambient occlusion attribute. Next, I want to add dirt to the terrain. I do this by using the Lab's Color Blend node. This node takes in an input mesh and an additional mesh to blend the colors of. It also takes in a mask to drive how the colors are blended. For the input mesh, I just feed in the terrain we've created so far with no dirt. For the second mesh, I want to feed in the dirt color. I first use an attribute noise to create an attribute to drive color variation in the dirt. Then, I use a wrangle to apply color from this ramp based on that attribute. I use the Lab's Adjust Color alias to tweak the color. This is just an alias to the attribute Adjust Color node with some more convenient defaults. I multiply in a constant color and tweak the saturation and value. Then, I color blend this with the original terrain color before doing the actual color blend, so I can apply the tool's dirt intensity parameter. I could also do this by driving the blend amount in the second color blend. But personally, when I'm in the tool, I like the ability to preview the dirt color applied uniformly to the whole mesh. Next, let's look at how I create the dirt mask that drives the color blend. First, I again use the Lab's Physical Ambient Occlusion node to get ambient occlusion. I set it to the dirt buildup mode, which creates nice values for approximating where dirt might build up in crevices of a mesh. If I turn on visualization of this dirt mask, you can see that it's much more intense in the places where you might expect dirt to build up. I then use an attribute blur to relax these values a bit. If I were to apply the dirt mask as it is right now, you'll notice that there's a lot of dirt sort of creeping up the rocks, which feels unnatural because dirt in those places would probably just slide down and off the rocks. In order to get this better effect, where dirt is lying more heavily in flat areas, I use the Lab's Calculate Slope node. If I visualize slope, you can see that this node is creating an attribute for how steep the mesh is. This is exactly what we need to get rid of the dirt on very steep areas of the rock. I do that by combining the existing dirt mask driven by AO with the new slope attribute in this node. If I visualize the dirt mask again, you can see that before this operation, the dirt is driven exclusively by where there are crevices, but after, the dirt is no longer on the heavily sloped areas. I again use an attribute blur to blur out these edges a bit, and then I use an attribute normalize float to ensure that the dirt mask stays in a 0 to 1 range. When I plug this into the color blend, I get good results of dirt that seems to accumulate in crevices, but not on heavily sloped areas. This switch is connected to the Has Dirt toggle, so if the user wants, they can bypass this addition of dirt. Next, I add the grass to the terrain. I do this in a similar way to how I added the dirt, where I start with an attribute noise that gets remapped to color. I then adjust that color and blend it with the original terrain, and then use a mask to drive how it's combined with the original terrain. This mask is generated in a similar way to how I created the dirt mask, except I don't use any AO information, and instead of measuring the slope relative to the y-axis, I let the user set what direction the slope is compared to. This means that the user can get a more directional effect for their grass, which adds some interesting variation to the terrain. If I visualize the mask, you can more easily see how this direction will affect the final grass placement. I also add 2 passes of noise to this mask, one large-scale noise and 1 small scale noise. These help break up the grass a bit. Then I again use an attribute normalize float to make sure that the mask still stays in a 0 to 1 range after the noise. Putting this all together with the color blend, I get this final result. Again, there's a switch node in case the user wants to disable the grass. Finally, I have another attribute adjust color, which I use to tweak the saturation, value, brightness, and contrast of the final texture. At this point, I also merge in an attribute that'll drive the terrain's roughness, which I create in this network box. Let's quickly walk through how this roughness is generated. Note that I create this roughness using color attributes until the very end, where I use this wrangle to convert the color to an attribute called roughness. I start by creating some large and then small scale noise to vary the roughness over the whole terrain. I use an attribute remap to clamp the roughness to a 0.7 to 1 range, because overall I want the terrain to be pretty rough. With this second remap, I clamp this roughness to an even higher 0.9 to 1 range, and then I blend these roughnesses together using the dirt mask, so that the places with more dirt will be extra rough. I then do a similar process, applying a different noise to the roughness in regions with grass, and then finally convert the color to roughness. This roughness attribute will eventually be baked out as a roughness map, but before baking the textures, I need to create the lower poly terrain mesh that we'll actually use in render. I do this by using a poly reduce, so you can see when I disable it and enable it, it takes this very high resolution mesh to a lower poly one. Then, I use the Labs Auto UV node to automatically UV unwrap this mesh. For this terrain, I don't really care what the UVs look like, because I already created colors that look good on the mesh, so as long as the UVs have no overlaps, I should be able to bake them just fine to any UVs. In order to ensure the UVs have no overlaps, I use the Labs UV Remove Overlap node. If I preview the UVs, I can see that I have no overlaps, so we're good to bake the textures. In order to bake the textures, I use the Labs Maps Baker. On the leftmost input, the Maps Baker takes in a low-resolution UV'd mesh. On the middle input, it takes in a high-resolution mesh with the attributes that you want to bake to the low-resolution one. So in the first input, I plug in my low-poly UV'd mesh, and in the second input, I plug in the mesh that I've colored and added roughness to. On the Labs Maps Baker, I've checked roughness and color, so maps for these two attributes will be baked out. Notice the output directory is driven by the terrain shader tool settings, so the user can easily change where these textures are baked to. I also set the tracing mode to nearest surface, instead of the default of surface normal, to avoid artifacts in places with sharp angles and deep crevices. The one little gotcha I want to point out about my setup is in the Materials tab on my Terrain Shader tool, I have this Render Maps button, which is hooked up to the Render button of the Maps Baker. However, for some reason, when my HDA is locked, this button doesn't work. So I have to allow editing of contents of the HDA to unlock it before hitting this Render Maps button. I'm not sure why this is the case, but it's such a niche and specific bug that it's probably low priority for labs to resolve. So you might also encounter this if you're using my tool. Finally, I revert the original transforms of the terrain, and then these last few nodes apply the shading mode options set in the terrain shader's parameters. Just like the wall generator, I have one option to create material overrides that'll automatically apply the rendered textures to the mesh at render time, as long as the shader with base color texturing and roughness texturing enabled is applied to it. The other option is to instead create a group for the geometry, so it can easily be separated for manual shader assignment later. Then, I just output the mesh with the appropriate attributes or groups assigned. This branch here on the right is responsible for outputting the color preview that comes out of the terrain shader's second output. It just takes the colored high poly mesh, reverts its original transforms, and then adds normals, deletes any extra attributes, and outputs it. You may have noticed that I don't create or assign any displacement in the terrain shading tool. This is because I want pretty high resolution, finely detailed displacement on the terrain. And to generate that kind of resolution in SOPs, I would need to create an insanely high resolution mesh. So instead, I just generate some noise and cops and apply this to the mesh. Note that unlike the base color and roughness texture, which respect the mesh's UVs, this displacement texture is just a random noise image. But because the displacement I apply is so small, you don't really see any seams in the final render. So even though this isn't a perfect setup, it worked well enough for my purposes. And that's it for the terrain shading. That wraps up the final video in this series breaking down the process behind Caelus. Again, the tools I made aren't perfect and could 100% be made more efficient and robust, but I hope they give you some inspiration for how you might tackle similar projects and how Labs tools might improve your workflows. I really enjoyed creating this project over the last 2 months of my internship, and I hope you enjoyed getting a peek at it too. Although my internship at SideFX is coming to an end, I do plan on starting my own YouTube channel for sharing more of my Houdini projects. So feel free to check that out if you're interested in seeing more projects like this. Thanks for watching!